Today we will be looking at geometric probability, but in one dimension and time. So this is going to be one dimensional and time probabilities. Okay, so one dimension, just like its name implies, we're just concerned about a length or a width. So for example, let's say that a road is 3 meters wide. Road is 3 meters wide, and there's a man here who is blindfolded. And he's walking this way. And let's say that we cross a red line here, or we draw a red line that is 1.3 meters long. Then if this man is moving randomly along this road, what would be the probability that he will cross the red line? And to solve this probability, it's actually the same concept as you would any probability. Now you'll notice that the road is not one-dimensional. This is actually 2 dimensions, but we're just concerned about the one dimension of this road. Namely, we're not really concerned about how far this man walks this way. We're just concerned about this distance here because we're concerned what is the probability that he will go through this portion of that road between the red lines, right? So we want to know again, for any probability, it's the total possible outcome, and then on top would be the desired outcome. So the possible outcome, the possible width that he can walk through is 3 meters in this case. This is the possible outcome. And the desired outcome, we want to find the probability that that man will walk through that line there. And that line is just 1.3 meters. So that would be our probability, 1.3 divided by 3. And that's going to give us 0.43 repeating. So the probability would be about 43%. There's about a 43% chance that this man is going to cross that line. Now, again, we are assuming that this action is totally random. That's why I've said that the man is blindfolded. If we put this line towards the center and that man is aiming to evade that line by walking towards the edge of the wall, then that probability is going to be much lower. It's almost going to be 0, in fact, if that man just walks along the wall there. But if the action is random, then we don't really know where that man is going to end up. So given that the action is random, this would be the probability that that man will walk through that line. Now we can do something very similar to time as well. Now it looks one dimensions and time looks different, but the concept is actually the same. So let's say a man is going to a train station, and at the train station, the train arrives and leaves during this time. So it arrives at 1 and leaves at 1:05, and then the next train comes at 1:20 and then leaves at 1:25, and then the train after that comes at 1:40 and then leaves at 1:45. So the train comes in 3 times during 1 o'clock and 2 o'clock. So if a man comes to the train station at a random time between 1 and 2, what is the probability that he'll be able to catch the train? Okay, so again, it's going to be the possible outcomes and the desired outcome. So the possible time that we're looking at is between 1 and 2. This is the total sample space that we're looking at. And since these are all measured in minutes, we'll go ahead and convert that to minutes. So that's going to be 60 minutes. There's a time frame of 60 minutes between which we're looking at. And the desired outcome between those 60 minutes is the 5 minutes here. This is when the train comes. The 5 minutes here, and the 5 minutes here. So there are 3 instances, and each of those 3 instances, the train stays here for 5 minutes. So on the numerator, we're adding those times together. The total desired time is 5 plus 5 plus 5, because those are the times when the train is actually here. So if a man walks in randomly between 1 and 2 into a train station, the probability that he will catch the train is going to be 15 out of, should write minutes here, 15 out of 60, or 1/4, or 25%. So there's a 25% chance, or 1 in 4 chance, that the man will catch the train if he walks into the train station randomly between 1 and 2. And again, the key word here is randomly. If the man actually plans to catch the train and comes in, or desires to come in at 1:20, obviously he's much more likely to catch the train than 1 in 4 times. Okay, but for simplicity's sake, we are assuming that all the actions done here are random.